Okay, the statistical sampling for optimization or solutions of something that's a big problem. Okay, a big problem that we don't know how to correctly sample or things. Okay, these are Monte Carlo method we have been dealing with. So from the last example, you use the Monte Carlo, have a rejection rule. Okay, rejection rule of the previous assignment. Okay, we can calculate pi. You roughly understand, okay, how slow, okay, not how fast it converges. Okay, so this is things that hopefully getting some initial experience with this statistical method for making evaluations. Okay, so today I'm going to finish the implications and tell you a little bit more variations in the statistical sampling. Okay, and I'll end up on the way how Monte Carlo is applied to choices of the numerical annealing. Okay. Okay, so we'll go for that. Okay, so you have seen that we use the random number. Okay, the random number that the generations usually is from a function. Okay, in your supported language. Okay, called random this. Okay, something like that. It should return. Okay, if they have your platform dependent how random is distributed, but it should give you a uniform distribution. If it's not 0 and 1, it's between 0 and the max integer, okay, just mode it, okay, just divided by that your right bound, and you can get a uniformly distributed random number. The mean is 0.5, okay. Mean is 0.5, variance is 1 over 12, okay. Mean is not 1. Yeah, so this 0.5. Any segment, okay, there are additional important thing, okay. Any segment of the number sequence will have no correlation with the other, okay. And the sequence is unpredictable, okay, and there's no memory effect, okay. It is like rolling your dice, okay, that you get a lot of threes in that dice. If the dice is fair, the chance of you getting a 3 in the next is still 1/6. It's not. There's no memory effect in any of the sequence. Okay. So most of such functions, what implemented in the language is only pseudo-random. Okay. They use an algorithm, something like this. Okay. This is one of the algorithms that's been used. So it uses a very large prime number times a seed, okay, and making this iteration several times, and then you get your next random number. Okay, the seed is usually coming from a program counter. Okay, so which is a integer that's not really predictable. Okay, not really predictable. So that's what used. But once you use the seed, and these A and C and M are fixed prime numbers. That means if you use the same seed, then all the sequence will be the same. Right? It's only pseudo-random. It appears as random, but it's not truly random, because if you use this kind of computation to generate it, if you somehow happen to have the same seed, okay, the same xi2 starts, and then everything will be the same, in the next. This will generate a bias in your Monte Carlo method. Okay, this I call a absolute death in communication protocol. Okay, many of the protocol like Aloha or many of the during the polling stage of asking who is around. Okay, it's based on random numbers. Okay, based on random, you generate a random number to decide whose term it is for you to listen. If two persons always give the same random number, they are forever collide, and forever collide you cannot resolve it. Okay, so that's the but it's the same thing happens in Monte Carlo. Okay, if the random number is a sequence that's always carried in certain ways, then there is a bias introduced in your sampling, and it's hard, case by case, how that bias will affect your conclusion. Okay, so this is also that you can believe that how good is this is probably satisfy the first two property easily. Okay, but because it's generated from the sequence, it is not true for the next two criteria when you get a random number from your language. Okay, from your language. Indeed, from the very beginning, John von Neumann says, if you think that this is true random number, and you can do anyway, if you think your computer can generate a random number, you are in a state of sin. Okay, you're kidding yourself. Okay, so that's not possible. Okay, so as long as you use computation to generate the sequence of random numbers, it's never that random. Okay, it's very clear to John von Neumann, which may not be clear to us. Okay, but it's true. Okay, that's the okay. So there are true random number generators. Okay, that has to based on physical effects. Okay, so these are many of the newer central processing unit start to give you these kind of random numbers, true random numbers. In Monte Carlo is introduce you a bias, but in many encryptions and communication protocol, if your random number is predictable, it's absolute death. Okay, so that many of the central processing unit start to implement circuits that can sample the true random numbers. Okay, either from thermal noise. Okay, that you build an oscillator, and the oscillator the input is noise, and the gain is so huge, and then you don't know what is the number, okay, because what is the final number is determined by the thermal noise. Okay, so this is vulnerable to a nitrogen spraying attack, and this is real. Okay, that the people knowing that you are doing this kind of random number, and they want to break that protocol, right? Saying your encryption most is a key and a random number. You do an exclusive OR to let people to avoid the replay attack. Okay, but if I know your random number always, then I can retrieve your key. That is broken. Okay, so that so people typically do, if you know the random number is from thermal noise, they spray liquid nitrogen on the CPU. This actually happened. Okay, spray, and then when the thermal noise is so small, the number you generate is just from process variation. Okay, so it becomes a predictable sequence. Okay, so thermal noise is something that's but it's used the most though. Okay, most of the processing unit today, if they give you true random number instead of random number from this kind of computed sequence, okay, thermal noise is the one that used the most. Okay, but they are vulnerable to this nitrogen spray attack. Okay, the next one being using is called single particle noise. Okay, this is also called the random telegraph noise. Okay, and it's one of the example I show here. And this is the things that actually my group has been doing. Okay, instead of going for the extreme quantum noises, difficult to get based on uncertainty principles, single particle noises are easy to get. Okay, it's not as good, as uncertain as quantum noises, but this is good enough. Okay, most of the time you can extract the random telegraph noise, then you can use that as a true random number generator. Okay, it's based on a uncertain. You have a single particle. The probability that it get trapped or not trapped is something you cannot predict. Okay, this is why it's called random telegraph noise is the statistical noise you hear on the radio. Where does that come from? That comes from something with a charge moving in space interfere with your radio. That thing cannot be predicted. Okay, so you can use that. But all this, you have some uncertainty. There's usually a debiasing part, right? Because you get a true random number from the physical effect. It may not satisfy these two criteria. Right? It's truly random. It's unpredictable. But the distribution may not be the distribution you would like it to be. Right? So thermal noise following its own Boltzmann distributions. A random telegraph noise follow its own distributions. Okay, physical distribution, it may not satisfy this too. So for true random number, you need to do this debiasing step. Okay, we need to do debiasing anyway. Okay, when you try to use the Monte Carlo, you want to guess, right? What is the random variable? What is susceptible? You are guessing its distribution function. It's not a uniform distribution function. Okay, so you need to do transforming between two distribution functions anyway. Okay, so this debiasing is something that not only usable for when we try to extract the true random numbers, but in Monte Carlo, basically what you're doing, you are doing debiasing, right? Because the V that you are testing may not be following a uniform distribution. So you wanted to follow your guess distributions. That's something you have to transform between two distribution functions. I'll show you how to do that, okay? And that's actually the critical step in the Monte Carlo. It's just that how do I get the most efficient guess of the unknown distribution? Okay, let me show you examples, okay? So now, if we have a random number, we know it's following a distribution, okay? And I need to generate random number with that mean and variance in our mind, okay? A certain distribution that we have, okay? So we need that random number in Monte Carlo, right? In some distribution, not the uniform distribution. Okay, how do we do that? Okay, so say for sampling of a gas, you are simulating the gas molecules and how the gas molecules cause different physical phenomena. Okay, you're generating random number to describe the motion of the molecule. Okay, the molecule now is going forward or going backward or going up, going down. Okay, you use random number to do that. But we know the physical law saying that it has to follow Boltzmann distribution. So I need to generate a random number that's close to Boltzmann distribution. Okay, so how do you transform from the uniform distribution in your computer Monte Carlo simulation that I can call my language to get a random number, but that's uniformly distributed, to another distribution function, okay, is the procedure I'm going to introduce to you, okay? Procedure is simple, okay? Together with the definitions of this CDF, okay, cumulative distribution function, okay? It's nothing but from minus infinity to present integration of V, right, of your probability density function. So P is the probability density. Okay, tell you the probability of when V, the probability for it to happen. CDF is integration, first integration of that. Okay, for sure, then you all know that FV, right? FV for it will go to 1, right? When this V go to infinity, it will go to 1. It start from 0 and go to 1. Okay, so regardless of whatever this P is, right? That F infinity will approach 1. This is just normalization, right? Your P, if your P is properly normalized, right? This is always true, right? So that is summarized here, okay? So we know that our P and F will be between 0 and 1, okay? Minus infinity, this is 0. Infinity, this is 1, okay? And this is, and FV is always monotonically increasing, right? You have a PV can follow whatever, okay? But your FV is always monotonic like this, right? Yes?
Are we assuming that V is like a continuous random variable?
Don't have to. Don't have to at all. It can be discrete. So it's just that it's a delta function in each instance, right? So if you have a V and PV, it's actually something like this. Totally fine. So then this will be steps, right? Yeah. So it doesn't need to be continuous. Apply to discrete just the same way. Okay. So this is a transformation, okay? So if you generate a random number, between 0 and 1. You map it to its very boring CDF. CDF of a uniform distribution is nothing but a straight line, okay? For sure, first integration, okay? You map this number to a known, the distribution, the CDF you desire to have, right? And then you pipe it down. This is the mapping to, this is your desired CDF. This is a probability density, okay? So this point, okay, this is not necessary. This is taking the first differential derivative of this one, but this is not needed. You just take this point, and this is the number, the random number that you need. Okay, so random number with the uniform distributions, map its CDF, and the random variable that gives you that this mapping is the desirable random variable that gives you the desirable CDF. Okay, totally reasonable. Okay, let's find a case. If your if this one, right, if in this mapping, this one doesn't even have to be uniform. Okay, this one can be anything. Okay, you generate a random number following any distribution. Once you have its probability density function and FV, to transfer it to another random variable, you just go through the process. That's it. Okay, this one doesn't need to be a random variable, uniformly distributed. Okay, it's just more convenient. Let's take a case when here is almost like the probability is very, very low. Okay, so this probability very low will be corresponding to a very flat region in your FV, right? So because you integrate, the probability is so low, so it will not increase your accumulative function. Okay, then it's hardly being able to map on that. Okay, so any function that is any probability that's small is flat, right? When it's flat, it will not be going through this mapping. So it will not just that. A intuitive understanding, okay? Intuitive understanding. The mathematical procedure is this, okay? Get a U. We know that this distribution function is this, right? Fu equal to U. Okay, find a V that's corresponding to this, right? You get your random number, okay? Let's practice, okay? Practice once, okay? So if I have I want to generate a random number, a random variable, or random variable V, that follow this distribution, okay? So this distribution is something like this, okay? Some exponential, okay? With lambda for sure here is the normalization. So this is a normalized distribution functions, okay? And we know all the closed form, okay? So this closed form is known, so we'll be able to evaluate f minus 1. So the V is just f minus 1 u, right? So you can actually analytically get this. Okay, so let's write a program. Okay, so you can generate a V that follow this distribution. In order to see that, okay, you are going to generate 1,000 instances of this variable. Okay, sort it and plot out this. Okay, and this one should look like this, right? Let's follow it once. Okay, so that you once you understand what it's doing, this is not hard. Okay, that means you get a V, get a U, which is nothing but your uniform distributed from the random function call. You go through this formula, okay, you will get a V. This V will, you generate 1,000 of them, it will actually follow this distribution. Try it, okay? Try.
Wait, how are you getting the
U? This U is what you get from random, a uniform distribution.
Right.
Right? In your computer code, right? U equals to random.
Oh, I see.
Right?
And then you calculate V.
Calculate V, right? Then V will supposedly, right, through our procedure, V will have this distribution function.
Right.
How do you plot it, right? You generate 1,000 of V, right? Sort it, right? Then you can get the probability density function, right? So just let's practice, okay? This is, yes?
didn't get that part. How can we equate the cumulative distribution function to U?
Fv is equal to U, right? So I map the CDF of the uniform distribution functions and the desirable distribution function. This is where it's matched, right? After that, so this Fv is equal to U. Okay, so now the goal is to find V, right? So it's F minus, the inverse of F, U is the function, right? It's the variable.
So, cumulative distribution function of any distribution would be equal to uniform distribution then? Can we say that? Or?
For that, at this evaluation, yes.
Okay.
Yes. So you transform your uniform distributions to this CDF. Let's try it. Okay. This is actually something that Monte Carlo, you do it every day. Okay. And this is a known CDF, right? This is a known closed form CDF. So you actually can implement this. Okay. Mapping of that is nothing but finding this, right? This is your uniform distribution function, right? So you F minus 1, F is coming from, in here is nothing but a known CDF, okay? So I can generate a random variable, have CDF, that's F. Or probability density function, that's P. Okay. Try it once, okay? Simple program for this case. So after the very simple transformation, the 1000V you get after sorting, maybe something look like this, okay? This is the thousands of instances after sorting. Then you do the bin, right? So this bin, the first bin from 0 to 0.5 is 3. The second bin is 1. Third bin is 3. And this is how you plot your 0.5, 1, 1.5, right? 3, 2, 3, 3, 1, 3. So this is the approximate piece of E. Okay. Feel free to use any kind of sort to plot out your distribution function.
Can we do plotting in C++?
Or you can just tabulate it. You should see this shape, right? So in the first being, the number should be large, right? It gradually decrease, right? That's another reason that C++ does not have a direct graphical library. So it's many times for visualization, you need something to process this data. Right? There are many. MATLAB is one choice. Okay, MATLAB for sure is. No, there are TICO, there are Java actually have reasonable graphic library, right? So you can. Sure. So that's one of the deficiency in C++. The graphic library is never unified. You have to, yeah. But for now, it just tabulate it. You should see this exponential decay. Okay. If a procedure is correct, okay, you should see that very clearly. Okay. For some students, this may be boring. For some students, this may be something you are not comfortable. Okay, I do find student distributions, students who like deterministic approach, and students like statistical approach, and students who are afraid of deterministic approach, and students who are afraid of probabilistic approach. Okay, statistical approach. So this one is statistical. Okay, so this part is straightforward. Okay, but you are interpreting a random variable with its interpretation, right? With this bin sorting, okay, bin sorting. Okay. But I totally encourage you to be totally comfortable in the statistical world, okay? You take any engineering job, you will be living in the statistical world. Okay, you should use this, okay? So these, unfortunately, okay, many of these kind of tests, visualization is the one of the easiest verification. Okay. Can we think about it? Is there any way that is there another way for verification, knowing that what you calculate is correct? Let's brainstorm on this. If you get right this bin. Is there any way to not visualization, you can verify it? Your routine to generate your module of generating a random variable of any given distribution function. You would like to verify what you implement is correct. What can you do? You'll probably not be able to finish within the class, but let's propose ways that can be for verification. Anyway? How do you verify it? This is what you will see, right? After the procedure, after the bin sorting, this is what you have, right? This for sure. In here, it's unnormalized probability density function, right? If this one divided by 1,000, then it will be normalized, okay? But you have still samples, okay, of this. Okay? How do you verify it?
I guess you could sort of see the trend and make sure that the trend is like a downward.
See a trend. How do I see a trend? How do you teach a computer to see the trend?
Oh, right, because you're...
We actually just finished that, right? How do you say there's a particular trend I'm looking for in my computation? How do I find it? How do your computer recognize that trend? You recognize that trend by look at it. But in translating to the computer understanding, yeah?
Produce it like a different way.
What?
Produce it a different way and then see if the two results match.
Implement two different way of this function. Yeah. That's one test, okay? But you don't know whether your obtained p probability of your random variable is correct, right? But that's okay. Implementing two different ways of the same thing, right? Is always a way to check. But this less ideal. I want a longer loop, right? And then check whether something is consistent. That this can have a higher probability is error-free. What can I do? Of this known function, right? Okay, yes, okay. That's another way, okay, you can check the mean or the variance of this. Another way I think about, okay, is fit your PV into parameter extraction, right? See if I retrieve the lambda, right? Just test it, right? So you see the trend, but what is the trend? The trend in your eye is trained to see a exponential function with a decay that's normalized by lambda, right? That's what your eye try to see. Turn into the computer testing is you do a least square fit of that function, right? And you can retrieve your lambda, right? And how close is that lambda, okay? If you want to be even more test, so the trend of that trend, right? The more case you generate with V, the better will be the extraction to be lambda equal to 0.2. Okay? And that it should be proportional, the accuracy to 0.2 should be following the 1 over square root trend. Okay? Okay? But when you say your visualization, right? When the computer to understand some trend, many times is parameter extraction. I think that this is a function you will follow. Then what is the parameter in that function? Okay, is how computer will understand that function. Okay, so another way, okay, just using the generated V, using this one as the instance to feed into your least square fit. See if you can least square fit, getting back your lambda equals to 0.2. Okay, and for sure your extracted lambda will not be exactly 0.2. It should be something close to 0.2. You'll be closer and closer to 0.2 when these grow, right? When the number of random variable you generate grows. Okay, so that will complete the loop of the of your testing. Okay, anything goes wrong with, and this will independent of what this is, right? So you can have any normalized probability density function, okay? And if you go through that loop, as long as that probability density have a parameter, or 2 parameters or 3 parameters, right? Use that to generate your Monte Carlo case. Use a Monte Carlo case to go through the parameter extraction, least square, Okay, that's a good verification. Very similar to when you do the solving the matrix, right? You get a solution. Back substitute that solutions to see if that your residue factor is small. Okay, so if you walk through the loop of statistical extraction and then go through parameter optimizations, and then you can go back to evaluations of that whether your computation is correct. Okay, for a case that's not non-CDF, right? So this one is so easy that you can finish within the last 5 to 10 minutes, is that I know the form of this guy, right? This form is known, okay? But say if the form is unknown, okay? It's saying that the PV is this normal function, and I know that FV is this, but there's no closed form. What do you do? In your program, how do I generate random variable that have this particular distribution? This is still not very hard, right? Take a step back and think about it, right? What we do in here, all we need is samples for this, right? Samples for this. So what you need is a table, right? You have a V, and you know piece of V, right? Calculate it, and you know the corresponding this one, right? So you're generating this one from the points of interest. You generate this table, right? Every time you need to find, right? Every time you have an instance in here, right? That's your U, right? So figure out what is V by table lookup, right? And this works for a unknown closed form. Actually, if I only have rules to know what is this, like when you calculated pi, I know a rejection rule. That's good enough, right? Table lookup, rejection rules, or you know the exact way closed form, can all finish this transformation easily. Okay. What I need is just a map, right? Whatever the uniform generated CDF map with this, right? What is the corresponding random variable? I'm done. Right? So I just need that table. This table can be generated from a known function, unknown function, or a rejection rule, something. Okay. As long as this table is there, you can go generate random variable according to this distribution function. Okay. Okay. So let's now to the use of this Monte Carlo. Okay, is something that gives you a confidence interval. Okay, saying that I can use Monte Carlo to generate a V that is my desired piece of V. The probability is the desired piece of V, right? Once you have these samples, okay, you can use it to do any evaluations that's interesting. Okay, you can do once you have V according to the probability you have. Okay, once you have this, right? You can use this to understand for sure V PV. Right? This is the average. Right? You can. That's equivalently. This will be right. You can use this to understand this. Right? You can do right. So this is nothing but your minus this, let's say this is A, right? You can evaluate the variance, okay? actually there are more. I can know not just the average. If I have a range I want to know, right? I'm asking what is the average within this range? You just choose the VI that satisfies this, you get the estimate. Right? How good is your estimate is described by this confidence interval. Right? When the number is large, I know my bias, which is the bias in the previous define, is your present random variable minus your present random variable generated average minus the true average, which we don't know. I know the bias follow the normal distributions eventually when I have enough samples. So this is what I'm doing, right? So if you in this range, the presently estimated average and the presently estimated standard deviation, this is my confidence level, right? Because it's my bias follow a random distributions. You can see that you want to know more, you need to have a large n so that within a short period or short instance, you have a lot of confidence. Right? 3 sigma confidence is this, right? 3 sigma confidence because the risk function is a normal function, right? So this is a 3. Within these intervals, that's you have this much confidence. Okay? And you take a step back and think about it, right? Many times, even you are not doing Monte Carlo, this is what you learn from the statistics anyway, right? Many of the social science behavior, you get sampling. You use those samples to make estimation. The only difference now is that those samples is generated by computer random distribution. That's the only difference, right? The way you sampled it, okay? In the true measurements, this is the same thing. Okay? But now I just have a way the computer can generate those statistics for you. That's all there is. Okay? So all what you learn this is in your statistic course. Okay? When you have a normal distributions and the theory, all the same theory follows, right? So if I sample any phenomenon as the number is large, the distribution function will eventually approach a normal function. And that's how you define your confidence level. Okay? So this is not part of your Monte Carlo. This is just that for any testing, right? This is true. Okay? Testing, this is true. Okay. So let's see how to apply it. Okay? So say Monte Carlo for initial gas generation. Okay? Saying that you have a parameter extractions that you'd like to do. The objective function have 20 parameters. Okay? Before we say each 20 parameters have, if you have 4 gases, right? If you have 4 possible values, the initial sampling, initial gas is way too much for you to handle, right? This number is too large. Even each parameter only have 4 possible guesses. Okay? You can use Monte Carlo to generate that, right? So we think that all these use random number, use it 20 times. If each parameter have a guessed distribution, or if you don't know anything about the parameter, you can guess that the parameter have a uniform distribution within certain range. Okay, and you use that to generate, right? You use Monte Carlo to generate those initial 20 parameters. Now it's not a search of this space. Okay. You can generate, say, the first 300 gases, right? By the Monte Carlo things, okay? And those gases is only as good as you know about the distribution functions of each parameter. Okay? That's only as good, okay? So if you know anything better about those parameters, is improve the gases you generate. If you know nothing, you just a uniformly distributed things, it's still better than a full search of this, right? It's just that this is the given time you have to generate those initial gases. Okay, I can do 300 gases. Okay, and these 300 gases is distributed among this huge space. And if I increase this number, I can get better and better coverage. But this makes my original problem to be now computationally practical. Okay, you want it better? You need to know, you have some knowledge about the distribution of your parameters that will improve your guess. Okay, if you're blind, just say it is uniform. Okay, then the gases are a random guess. Okay, doesn't improve the confidence dramatically. But even if you generate a lot of these cases, right? So if these become 10 to the 6, no, this is it's still pretty good. The n is now rather large, right? It's still much smaller than the full search, right? This is something that's the computationally practical. Okay, so you can use Monte Carlo to generate initial guess. Okay. Okay. So the next very important applications is on simulated annealing. Okay, this will be the last topic, and we'll be finally leaving the topic of the nonlinear software and optimization. Okay, but I'm not going to give you simulated annealing is pretty new. Okay, it's less than 35 years. Okay, it's nice, the only reason. But the idea is simple. Okay, the idea is that annealing, like you want to get diamonds. Okay, you just have to heat your carbon, your soot, to very, very high temperature, applying the correct pressure, and then cool it down. Okay, you need the temperature to raise it, okay, to randomize it. Okay, so and then cool it down, right? So annealing is the process that you assign a very high temperature, randomize everything, right? Kind of your Monte Carlo generating many samples, okay, and then let it cool down, right? Restrict the search gradually. Okay, that's annealing. Okay, annealing in physical sense. For sure, in today we still don't know how to make diamonds. Okay. In a large scale, okay, so the man-made diamond is still of a poor quality, simply because even that, nature doesn't do such a great job. So your simulated annealing is limited ability, okay, limited ability. But it's many times the only thing we can use, okay. So how do we do a tied to Monte Carlo, okay? So in your line search, okay, whenever you solve a optimization problem, you get a correction direction, right? Either from Newton solver, from your Jacobian inverse or your Jacobian matrix, or it's a steep descent, right? You come in from the previous step, okay? You do the steepest direction. You get a correction factor direction, okay? And you are ready to do line search. And when you do line search, when there's no further improvement you can find, okay? That's a minimum. Right? So when you get your correction, and the correction is close to 0, and you perturb the corrections, the correction is close to 0, you perturb the search directions, is you cannot find any better improvement. So that's a local minimum. Okay, you can record that local minimum, or you can just assign, I perturbed that anyway. Okay, I perturb this delta V. Delta V is from my line search, right? This T, right? And this probability of T, it's follow this distribution. What is that? Okay, so this, now you have a T, right? A parameter, right? So you will get a large T, kick it out very far away, only if when T is high, right? So this is a finite number, okay? When T is very large, right, that is the only time that T can be of any significant number, right? Or else T will be close. If T is very small, okay, then the T that's being generated will always be very close to 0, right? The only way that you will have a significant step size is when T is large. Okay, so you can control. Okay, so in your line search, that you can control this T, okay, to search for your global minimum. Okay, each time I'm not taking just the minimum I have reached now, but I go through this annealing step, assign a temperature, okay? And when T is large, then even when I don't know how to improve that, I kick it out far. Okay? This is a step, okay? When T is very large, then there's large penalty on this delta has a higher probability to be taken, okay? When T is nearly 0, right, you can only take very small step, right? In this function, when T is very 0, this is so huge, right? This is a huge number. That means this is very small. Right? This exponential term become very small when T is very small. Okay, so then you are. That's when T is closest to 0. You cannot take any heavy penalty. Okay, so T is large. It's like I heat up the material, right? When T gradually becomes smaller, I restrict the way I can be kicked out of the local minimum. And I'm done, okay? So this is something, so you can imagining, okay, the strategy of setting T in your search, right? Initially, I set a very large temperature. So whenever I reach a minimum, local minimum, it's very likely I take a large step to kick it out. And then you start search again, okay? Search and things, right? But you gradually make the T, the capital T, smaller and smaller to quench it, okay? Hopefully, it will be going to a true global minimum, okay? But just like in nature, okay? When you heat up the soot, high temperature, and you cool it down, most likely you still getting soot, not diamond, okay? Only the very detailed engineering practice with all the correct temperature and pressure steps, you get diamonds. So in hope of just this strategy to get diamond or get the true solutions, very minimal, okay? It still goes back how much you understand the problem. Okay? If you don't understand, just believing your artificial intelligence or machine learning or something that can really bring up the stage, okay? It's like heating soot and cooling it down. Most of the time, if you don't do anything special, you're still getting soot, okay? Just those dark powder, okay? You're not getting diamond, okay? Diamond is always obtained from a detailed knowledge of the problem of your searching, okay? Don't get me wrong, okay? This still, that means how open is this artificial intelligence to set this T, okay? Today, we have limited understanding, meaning that we have a lot of room for future improvement. Okay, any questions? Now I'll close if you close your eye and think about it, we define the nonlinear solver. We define the equivalency of nonlinear solver to optimizations. In optimization, we introduce the parameter extractions and geometry, right? So how these map into the different applications, and finally we get statistical estimations. You can finish the loop generating the measurements directly from statistical distributions. If you want to verify it, you can do parameter extractions again. Okay, so this complete the loop of my optimization. Optimization deserves its own course. Okay, so endeavor on. Okay.